Hello, everybody. So what we're going to be looking at today is still section 10.3, which we started last time, um, but the second half, which is going to cover isomorphisms. So isomorphisms are an interesting topic. They're a good topic. They actually will help you in a wide variety of math classes if you know what isomorphism means. Um, and yeah, so it's a good topic for us to talk about in this class because you'll have a vague idea of what it is later on. So, what is it? So, the idea behind isomorphism is this. Isomorph is myomorphism. Oh, I was right. Okay. Okay. Isomorphism. Words are hard. Okay. So, what's the idea? So, just break the word apart, right? First, you've got iso. What's iso mean? It means the same, right? Maybe you know that from other science classes, right? So iso, same. What is morphism? Well, basically, like anything with the word morphic or morphism in, well, a lot of topics is going to mean like shape. So same shape. That's the idea, right? So isomorphism is same shape. What's that mean? Well, what it means is that two graphs are going to be basically the same. So there's going to be a definition, probably. Let's see here. Is there a definition? Oh, yeah, yeah. Okay. So there is going to be a specific definition, but the idea is going to be this. So when we say same shape, what we mean is basically they're the same graph that you drew two different ways. Basically, two graphs are isomorphic if they are really the same graph, drawn two different ways. No, not two different ways, two different ways. Now, that might seem like, silly that you're like, well, what does it mean that they're the same graph? Like, why do we even need a definition? Well, it's just that, some pictures look different. So if I draw a graph and I do this, right? Here's G and here's H. These are really the same graph. And you think like, okay, well, what does that really mean that they're the same graph? Well, look at it. If this is vertex A on this graph, and this is vertex A on this graph, then A is connected to two vertices, right? A is connected to this vertex. Let's call this one B. All right. So this one, what if it's connected to? Connected to a vertex that we could call B. All right. And then from A to B, the next one you would go to, maybe we'll call it C. 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 And then C is connected to D, as I want it to be. And then D is connected to, I didn't label it, E. E. Um, D is connected to E, and then E back to A. D to E, E back to A. Right? So you see that actually these are the same, right? If you just trace through the graph, um, both of these graphs are actually what we called C5, right? Both graphs are C5, really. Or at least they're isomorphic to C5. Okay. And so they're drawn with different pictures, but they're actually the same graph, right? Because C5 had a definition, right? It was like v1 to v2 to v3 to v4 to v5. And then when you get to the end, v5 back to v1. And same thing here, right? v1, v2, v3, v4, v5, and then back to v1. So it's just a different picture for the same graph. And that's all we mean when we're talking about an isomorphism. Now, hopefully, one thing you noticed is that it might actually be hard to tell that two graphs are isomorphic, right? Like you might not have looked at this star and looked at, this pentagon and said, oh, right, they're really the same. It's not easy to tell if graphs are isomorphic, and we're going to see that pretty soon. Generally, what we're going to do is we're not going to show that graphs are isomorphic. We're going to show that graphs are not isomorphic because it's just easier. So let's actually have a definition of isomorphism now, and then we can do some stuff with it. Definition. So we need two simple graphs. I mean, they don't have to be simple, but we're just going to restrict this definition to simple graphs. So the simple graphs, G1, which vertices and edges, and G2, which is also going to have vertices and edges, are isomorphic if there is a one-to-one function from, well, they call it f, from v1 to v2 with the property that A and B, which are vertices, so A and B are adjacent in G1, if and only if f of A is adjacent to f of B in G2. Okay. So then the function f is called an isomorphism. And two graphs are either isomorphic or they're non-isomorphic. So there's no third possibility is what I'm saying here. So two graphs, you just say isomorphic or non-isomorphic, right? Now that's a complicated definition. But basically all we're saying here is like, if I go back up to this picture and let me erase, oops, not that. Back up. So like if I numbered the vertices like this, like V1, V2, V3, V4, V5, like that, then actually let me copy this. We can write it, duplicate it, move it down here. We'll use this as an example right now. Example. So these two graphs are isomorphic and we need to come up with the function. So these are isomorphic because here is a one-to-one function that, and I'm going to say, this is the first time we're saying it, preserves all edges. I'm just going to say preserves edges. Okay, that's going to be good enough. Now, what do I mean by that? Like, what is the function? So it's actually far simpler than you probably expect it to be, right? So here's the idea. So you just say, okay, um, so f of a, f of b, f of c, f of d, f of e, right? So your function takes in all your vertices, right? These are all vertices of one of your graphs. Doesn't matter which one, actually, right? And then here you're going to have vertices of h. And what you're going to do is you pick what you want the output of this function to be. So all you're doing is every vertex over here is like one of the vertices over here. So you just pick one and then match it up. So there's lots of ways to do it. Probably you would expect me to do A is V1, but it doesn't matter. So let's do A is V4. In this case, it doesn't matter. So like, let's just say A is going to be the same thing as V4. Why? Because it'll work. Okay. So then what you have to do is kind of trace through this function, figure out what the implications of that would be. So like A is supposed to be adjacent to B and to E. Now over here, V4 is adjacent to V3 and V5. So what you have to do is you have to say like, okay, well, if V4 is adjacent to V3 and V5, and on the other graph, A is supposed to be adjacent to B and to E, then that means that like V5 is going to have to be B or E, and V3 is going to have to be, the other one. Because if A is adjacent to these two, then V4 needs to be adjacent to these two, and that has to match up with what we have here. So A is adjacent to B and E. V4 is V5 and V3. So you just say, okay, well, what are we going to do with that information? Well, I don't know. Let's say E is going to be V3, right? A goes down to E, V4 goes over to V3. There's something in the way. I can't click. Okay. So what did we say? V3, we said, let's do V3 is going to be E. So you come down here and say E is V3. And V4 is connected to V5. So the other one that A is connected to is B. So V5 must be B. Like that. And then you just continue this on. Like, so for example, how would we continue this on? Well, like here you have A is connected to B. B is connected to C, right? Let's pick a different color here, like red. So B is connected to C. Well, here B is V5, right? So this is our B, right? This is A, this is B. So this must be C, the equivalent of C, right? A, B, C, A, B, C. So this must be C. So V1. And then V1 is connected to V2. Here C is connected to D. Do I have more colors? Let's pick another color, blue. So D must be V2. And then just to, double check that we did this correctly, you go from C to D to E. Here you go C to D to V3. Oh, sorry, V1 to V2 to V3. So C, D, E, V1, V2, V3. This must be E. So E should be V3. Is it? E is V3. We already picked that. Okay. So basically every vertex on the left is like one of the vertices on the right, and you just have to decide how they are. We could have just gone V1, V2, V3, V4, V5, and that would have worked, but this also works. Maybe it would have been easier to start with the, simplest example. Um, okay. So technically, when you're finding an isomorphism, you are finding that function. So if they say that, so it's just note, if a problem says find the isomorphism, they mean write down the F like I did, like we just did. Okay. Now I want to do this one more time just to show you that I really made this more complicated than it needed to be. Let's just take the same one again. Duplicate. So it would have been far easier just to do this, right? Like we didn't have to get so complicated. You could have just started like this. If the vertices over here are A, B, C, D, E, and V1, V2, V3, V4, V5, what you could have done is just like pick a color, green here, and just say, okay, we have A. A looks to me, maybe A looks like V5, right? So I'll just go A. And then just follow around the graph. A connected to B, A connected to B. Let's call this B. A to B to C, A to B to C, must be C. A to B to C to D, A to B to C to D, this must be D. A to B to C to D to E, A to B to C to D to E, this must be E. And then just to double check, back at the beginning, uh, A, B, C, D, E back to A, B, C, D, E back to A. Yeah, so it all works, right? So if you just kind of go through this step where you just label like whatever the vertices are called on one of them, you start labeling the vertices over here with the same thing. And then when you're done, that's your function. So you just go like f of A is V5, move. Okay, like just A is V5, B is V1, C is V2, D is V3, E is V4. Stop. I keep getting notifications that you guys can't see, but I can see, and I can't click on what I need to click on if there's a notification. So then you just trace this around. So B is V1, V2, D is V3, E is V4. And again, this is a different isomorphism than we used before, but it doesn't matter. Sometimes there's many isomorphisms and sometimes there's only one. So this is another possible F. Point is, you can do it on the graph like this first and then just write it down when you're done. Okay, so let us do a different example here. So let's see here. Looking for some nice isomorphic graphs. I think these are here. Hopefully these are going to work. Um, so it's got a like this, like this, like this, like this. And then we got another one here, 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 here. And it goes like that, like that, like that, like that, like that, like that, like that. Okay. Ugly graphs. There they are. Okay, so we have labels here, U1, U2, U3, U4, U5, U6. And over here we have V1, V2, V3, V4, V5, V6. Okay, so we have not actually talked about how to tell if two graphs are isomorphic. The only thing we know is that you have to figure out what vertex is what vertex. And the way you would do that is, again, you're trying to identify which vertex is like which other vertex. So you can just pick somewhere. If you think these graphs are isomorphic, first of all, then what you're going to do is you're going to pick a vertex and just say, like, which vertex is it like? So you can pick any vertex here. Maybe we'll pick a corner vertex. Let's pick V or U4 here. Okay, so if you think these graphs are isomorphic, then so we think they are isomorphic. Now you might not, but we haven't really talked about how to tell, so we will later. We think they are isomorphic. So we try to come up with the F. So try to guess which vertices correspond to which other vertices. Which vertices in G match up with the ones in H. Okay, so that's what we're trying to do. So I picked this one, I called it U4, or it's called U4, and you would say, well, which vertex over here is like 4? And what we're going to learn, we're going to write it down, is that the way you want to do it is there's something that we call, what is it? There's something that we call invariants, which is things that don't change under isomorphism. So like, for example, the degree of U4 here is 3, right? 1, 2, 3 edges. So whatever it whatever it matches up with over here must also be degree 3, right? So U4 is definitely not V1 because V1 only has degree 2. Not only that, but there's other things. So you would say like, okay, so if this is degree 3, it could be V5. It could be V3. Doesn't really matter. Maybe it's one of them. So let's just say it's this one. Why not? The same corner, so let's do that. Okay, so we'll start trying to write this down. So let's F of U4 looks like V5. Okay, now then what you have to do is you say, okay, well, this is connected to U1 and U3. This is connected to, this is connected to U1, U5, and U3, right? 3 different ones. Here, it's connected to V1, V6, and V4. So there's 3 choices there. So let me pick a different color here. Pink, pink, pink. Well, those are here, here, and here. But which one's which? And that's where you have to start looking more carefully at the structure of the graph. So like looking at U4, U4 goes to this vertex, which has degree 2, to this vertex, which has degree 3. So you go degree 3 vertex to degree 2 vertex to a degree 3 vertex. If you try to follow this upward path, this is degree 3, this is degree 2. This should be the corner, right? Like if you go here, 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 that would be here, here, here. But V2 is definitely not U2, right? Hopefully you can see that because U2 has 3 and V2 has 2. So this can't be this corner, right? So if this cannot be this, V2 and U2, then V1 can't be U1, right? Because you go here, 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 that'd be here, here, here. This can't be this, all right? So you have to think about it, right? To get to this opposite corner over here, you have a path that goes like from here you go to this vertex to the corner, to this vertex to the corner. And this middle path goes to U5 to U6 and then to the corner, right? There's like two extra vertices on the way from here to here. Uh, well, here you should be able to see, hopefully, that the equivalent of this middle path is basically this top path here, right? Because this is the corner, lower left corner. This is the upper right corner. You can tell that because this is degree 3 and this is degree 3. So U2 must be V3. And then you have a path that goes 2 stops in the middle to the corner, 2 stops in the middle to the corner. So actually, if you're writing these down, the what is it, U5 there? F of U5, this vertex is actually the same as V1, right? Because this is on the 2 stops in the middle path. So V1. Okay, now what about the others? Well, we have U1, that's the other one, and we have what is it, 3. Well, when you're looking there, U1 is corner, like degree 3 up to a degree 2 over to a degree 3. And here we have V5 to a degree 2 to a degree 3. And also we have V5 to a degree 2 to a degree 3. So these two, V6 and V4, look like this one, U1 and U3. And I don't actually see a difference between these two and these two. Like, I don't know if V6 is supposed to be U1 or U3. It doesn't matter. V6 is just going to be one of them. So you just pick one. So U1, let's just let U1 could be V6, which would make U3 V4. All right, so we did 4 of them. What haven't we done? I guess just the corner one, right? So the last one is F of U2. That's the only one we have not done. Wait, no, that's not true, actually. And also, we haven't done U6. We haven't done U6. All right, so which one's which? Well, hopefully, again, we can do this by inspection. So following this middle path, it goes U4, U5, U6. There. And that's the top path here, V5, V1, V2. Those two match up. And then that would make U6 should be V2. And then finally, the only one we haven't looked at yet, the U2 must be the V3. Like that. And once you write this down, this F is the isomorphism. So G and H are isomorphic. To each other, you could say. Or just isomorphic. And we know they're isomorphic because the function is the isomorphism. So the fact that we were able to find the F, that meant they're isomorphic. Okay, now let's look at another one here. Yeah, okay, that'll work. Right, how are these called? A, B, C, D, E. This is called G. And here they're called A, B, C, D, E. And this is called H. All right. So are these isomorphic? What do you think? So I think they are not isomorphic, and I'll tell you why. I think they are not isomorphic because when I look at these two graphs, every vertex should be like on the left graph should be like the right graph, right? Every vertex needs a corresponding vertex. And so when I look at this, I see E here on H, and it's just hanging off by itself, right? E E is only adjacent to one other vertex. And I'm looking at G, and you would say, okay, well, where is the equivalent of E? Where is the vertex that only has one neighbor? And there isn't, right? So E only has one neighbor. Here, there is no corresponding vertex with only one neighbor. So I see that, and immediately I know that these are not isomorphic. You could not possibly find a function like we did here because already what over here matches up with E? Nothing. And that uses the concept of invariants, which I will explain as soon as I write this down. So, um, so I notice immediately that in H, um, vertex E has only one neighbor, but no vertices in G have only one neighbor. Right? So that's a big deal. That means that there's no the function won't like no isomorphism will be able to work because it won't be able to match a vertex to vertex E. Um, so no function can exist. Well, I'll just say no isomorphism can exist. That will, preserve all the adjacencies. And now, why would it need to do that? Well, because go back to the definition of isomorphism up here. So it says one-to-one function, which one-to-one means just every vertex in G matches up with one vertex in H. Um, property that A and B are adjacent in G if and only if f of A is adjacent to f of B. So what that means is if E is adjacent to only one vertex, then due to the one-to-one property that must preserve all those adjacencies, there must be a vertex over here that has only one neighbor, and there is none, right? E only is adjacent to one thing, so what over here is adjacent to only one thing? Nothing. So it doesn't work. All right, which leads us to what we were talking about, which is the concept of invariance. So let me try to find it. Yeah, okay. So so certain things must be true or at least equal in isomorphic graphs. Number one, they have to have the same number of vertices. Right? Hopefully that makes sense. Because you're mapping the vertices from one to the other. They must have the same number of edges. Why? Because of the same thing up here. We said that if vertices are adjacent over here, they need to be adjacent over here. That means if there's an edge over here, there's an edge over here. Has to be, right? And the whole thing here was E only has one edge coming from it. So something over here needs only one edge and it doesn't have it because these are not isomorphic. Okay, so they must have the same number of vertices. They must have the same number of edges. What else? Also, what we call the degree sequence must be the same. So like, for example, if you write out the degrees of every vertex and, write them in order, right? So like, if you have, if you write out the vertices, or actually, let's just use these two as an example, I guess. If you write out the degree of each vertex, we have, what do we have? 2, 2, 3, 2, 3, right? So 2, 2, 3, 2, 3. Or if we put it just in kind of ascending order, there's 2, 2, 2, 3, 3, right? 2, 2, 2, 3, 3. That was for G. And if you write it out for H, the degree of each vertex, we have 4, 2, 3, 2, 1. So if I just again write it in kind of ascending order, why? There's no reason, just so we can compare it easier. 1, 2, 2, 3, 4. 1, 2, 2, 3, 4. Right? So these could not possibly, the graph up there could not be isomorphic because, again, what we noticed was that H has a degree 1 vertex and G does not. That's what we noticed. We could have also noticed, this makes it obvious too, that H has a degree 4 and G doesn't. And when you know that, you can come up here and you can say, oh yeah, A has 1, 2, 3, 4. No equivalent over here. Okay. So in that example, um, the fact that, H has a degree 1 vertex or degree 4 and G doesn't automatically means that they are not isomorphic without doing any more work. All right. And so those are what we call invariants. So there's others, but those are the easiest ones to look for. And from there, you can get more complicated, like if you had to, like if you have a degree 1 adjacent to a degree 4. Over here, you would have to look for a degree 1 adjacent to a degree 4. And if that didn't happen, then they would not be isomorphic. Um, so let me see. Let's do one more example here. Uh, I'm not going to be super rigorous here because I'm out of time, but there's our G. H is going to be kind of the same picture. Got a ring all the way around the outside. Got a box in the middle. We got this and this. All right. So these are not isomorphic, and probably you can do it by writing, you can show that they're not isomorphic by writing all the degrees down. So like 2, 3, 2, 3, 3, 2, 3, 2, 3, 2, 2, 3, 3, 3, 2, 2. So if you write the degree sequences down, this one is, what do we got? 2, 2, 2, 2. So 4 twos, 2, 2, 2, 2, 3, 3, 3, 3. And here, if you write down the degree sequences, we got 2, 2, 2, 2. Still, so we still have 4 twos and 4 threes. 3, 3, 3, 3 when you write them down. So they are the same. But these are still not isomorphic. And from the picture, you kind of get the idea that they're not, just from the fact that um, this over here is on the opposite side here, and here they're right next to each other. But that's not, like, just noticing that in the picture isn't the same thing as a proof. We need a proof. So there needs to be some reason why this is the case. And so it's tricky to do, but you have to find something about these two graphs that shows they're not isomorphic. So you're looking for a vertex that doesn't have a corresponding vertex. So let's see, here's a degree 2 vertex that's connected to 2 degree 3s, right? A 2 and then a 3 and then a 3. So you say over here, you say, is there a degree 2 vertex that's connected to 2 degree 3 vertices? So this one is connected to 2 and 3. 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 I think I did it, right? So if I just highlight it, here's a vertex. It's a degree 2 vertex that's connected to a degree 3 and a degree 3. And over here, all of the degree 2 vertices, there's no degree 2 vertex that's adjacent to 2 degree 3s. This one's 3 and 2. This one's 2 and 3. This one's 2 and 3. This one's 2 and 3. So you see there's no corresponding vertex over here. So I notice that and say, we see G has a degree 2 vertex with 2 degree 3 neighbors. But H has no such vertex. So G and H are not isomorphic. All right, so that's more complicated than what we described up here as these simple ones, but it's still the kind of thing you have to do to show that two graphs are not isomorphic. All right, and so just one last thing before we go. The key here is this. You're looking for differences in the graphs to show that they're not isomorphic. If you want to show that they are isomorphic, you've got to find the function. So again, last tip. Tip 1. To show isomorphic, find the function. To show non-isomorphic, find something different in the graphs. Right? Using what we call invariants. which are, the things that don't change when you do an isomorphism, like degree sequence and like this kind of connectivity thing. All right, so that's it. I'll post this as soon as I can, and I will talk to you guys later.